Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over indicators, pH, and colors. So first of all, we need to understand what an indicator is. So an indicator is a substance that's going to change color depending on the pH of the solution that the indicator is in. And so indicators are basically they're organic acids themselves. So when you put them in water, they're going to dissociate or ionize, and then you're going to get an equilibrium. So here's a generic indicator. So you have indicator with the hydrogen on there. It's going to react with water, and then it's going to donate a hydrogen to the water, giving you the hydronium, and then you've got the conjugate base left over. And depending on whether it's got the hydrogen or not, it's going to give you the color. So if it's mainly in this, if it's in this state here, then you're going to get one color. And if it's in this state here, you're going to get another color. So this is what the color change is indicating. So the color of the solution is then going to depend on the relative concentrations of your acid, the indicator in the acid form versus indicator in the base form. So for example, if the ratio of the base indicator in the base form over the acid form is equal to 1, then that means you've got equal concentrations of the acid and base forms of the indicator. And so that means you're going to get an intermediate color. If the ratio here of the base over the acid form of your indicator is larger than 10, meaning that you have a larger amount, an amount or concentration of your base form that is greater than 10 times, greater than a factor of 10. If this is greater than by a factor of 10 than your acid form, then it's going to be the color of the base form of the indicator. So whatever the color of this base form would be is the color of the solution. If you have the opposite situation where the concentration of your acid form is 10 times greater or more than is greater than the base form of your indicator by greater than a factor of 10, that's going to give you, of course, a 0.1. If it's greater than this, then that means the solution is going to have the color of your acid form, so whatever that color is. And so you can see here that the color can change within a range of either a greater than a factor by a factor of 10 from 1. So when the solutions are equal, then you've got 1, and then so that's going to be intermediate color. If the base is greater than a factor of 10, then it's going to be the base color. If the acid color is greater than a factor of 10, then it's going to be the acid color. And so we can use the Henderson-Hasselbach equation to bring this out a little bit more. So if we write out the Henderson-Hasselbach equation, we know that pH is equal to the pKa plus the log of the base over the acid. So we can apply, since our indicator is an acid and we get an acid in base form, we get the acid in conjugate base, and this is an equilibrium, we can plug this in and get the relationships. So, but I want to go back here and stress a point that I want to make. So here, what's happening in the indicator? So first of all, we don't need a whole lot of indicator added to our solution. So the colors are so strong that you only need a tiny amount. So maybe 1 or 2 drops of an indicator is usually enough to get a color change, an obvious color change in your solution as the pH changes. And what happens when pH changes? So if I have this as an acid, let's say, for example, this is phenolphthalein. Phenolphthalein has a clear color when it's acidic. In acidic solution, it's going to have a clear color. and in basic solution it's going to turn pink. So what's going on there? So if this is our indicator, it itself is in equilibrium, right? So when it's in equilibrium, we can think of Le Chatelier's principle. And so Le Chatelier's principle tells us that if you change anything, then it's the equilibrium is going to shift in order to undo that change, or to decrease that stress, or that disturbance in the system. So here, for example, let's say we start with an acidic solution. So if we have a high concentration of this, so if we add a lot of this, then it's going to push it into this direction where the indicator has the hydrogen on it. So this indicator, this form of the indicator is going to be it's going to be more prevalent, right? So in this case, the color 1, an acidic solution, if this was phenolphthalein, then this is going to be clear. So it's going to be no color. If it was a different indicator, it might be some color, green, red, whatever the color is. So as you are doing your titration, right, so you're adding base to the titration, you're neutralizing the acid, you're making this disappear. So you're decreasing this as you're adding base. Well, if you're decreasing this, what does Le Chatelier's principle tell us? It tells us that it's going to shift in the direction to replenish, or try to undo that change. So it's going to try to increase this. So it's going to shift in this direction, and it's going to create more of this form, the conjugate base form of your indicator. So as the titration goes and you're adding more and more base, there's going to become a point where uh, the amount of this is going to be low enough, and the amount of this is going to be high enough that where they start to become more equal. And as we said here, if they're equal, then you get an intermediate color at this stage here. So if you start off with a lot more of this, then you're going to have a lot more of this in solution than your conjugate base, and so you're going to end up having the color of the acid form. So this would be prevalent. So you'd have this color. But as you do your titration and you're adding base, then you're decreasing the amount of this. It's going to shift this way. So this is going to decrease. This is going to increase. And so eventually you're going to get closer to 1, and you're going to reach that in the intermediate course. If you keep adding base, then eventually you're going to increase so much the indicator in the basic form compared to the indicator in the acid form. And so then you're going to get the color of the indicator in the basic form here. And so that's what's happening to get that color change. And so going back here to the Henderson-Hasselbach equation, since we've got the concentration of base over acid here, and we're looking at the concentration of acid and base here, we can put that into this equation. So here we have the pH is equal to pKa plus the log of the base form of the indicator divided by the concentration of the acid form of the indicator. And so if we rearrange our equation, if we bring the pKa over to this side, so we subtract both sides, we subtract the pKa from both sides, and so we get pH minus pKa is equal to the log of the base over the acid. And then if we undo the log, right? So if we raise everything to the power of 10, so then we get 10 to the power of pH minus pKa, and then we get this is equal to the ratio of the concentration of the indicator in the base form over the concentration of the indicator in the acid form. So now we can kind of see here what happens if pH is equal to pKa. Well, if pH and pKa are equal, and this is the pH of the solution. So if the pH of the solution is equal to the pKa of your indicator, then what happens is that this becomes 0, and 10 to the 0 power is 1, and that's what we have here. So if the pH is equal to pKa, then the ratio is going to be 1, and we're going to get the intermediate color. If, let's say that if the pH is equal to the pKa plus 1, right? So that means that the pKa plus 1, then what's going to happen is this is going to end up, the pKa's are going to cancel out, and you're going to get 1 for the coefficient, or I'm sorry, the exponent. And so that's going to be 10 to the 1 power, so that's going to be 10. And so if you look here, that would be this here. So if it's greater than 10, then the color of the indicator. So if pH is equal to pKa plus 1, then that means if it's the pH is greater than the pKa by 1, then you're going to get the color of the base form of your indicator. And then, of course, if the pH is equal to pKa minus 1, if we plug that in for pH, we get -1 for our exponent. So that means that the ratio here is equal to 10 minus 1, or 10 to the -1, which is the same as 0.1. And so here, that would indicate that the color is in the acid form here. So that would be when pH is equal to pKa minus 1. So you can get, if your solution, if the pH of the solution in a two-point range can change color in that transition. So you can change by like it would take 2 pH points on the pH scale to change the color. So the pKa plus or minus 1, if the pH changes within that range, you're going to get that color change there. So that's how the indicators work. And so you can choose an indicator that you know has a certain pKa, and if you have an idea of where the equivalence point is and where that pH is going to change, you can choose an indicator that would change within that range. So I hope this is helpful. If this made sense, if this clarified things for you, please like that, hit that like button, subscribe to my channel, and hit that notification bell so you can be notified by other videos that I put out. Put a comment down in the comment section. Let me know what you think, and if you have any questions. Thanks for joining me. Have a great day.